I was just writing down some notes so we can get started. It, it seems like no one has any questions, and everybody seems to be typing their first and last name in chat. I appreciate that. We got about 1 minute left. Anybody have any last second questions before we start?
I have a question real quick in regards to exam three and final exams. So, is
Yes,
exam three the last week of or not last week, the first week of December, then the following week is finals? Is that correct?
that sounds about right. I'd really need to check our syllabus for that, and I'm going there now. So let me see.
Okay.
Uh, far as the syllabus has written, yeah, it looks like our online tests, or excuse me, our face-to-face test three. Oh, I don't even see it on here. Maybe I'm looking at the wrong class. Nope, I am looking at the right class. Let's see what's going on then. Uh, holy crap. I must have put in a erroneous calendar in our syllabus because all of a sudden I don't see any face-to-face tests listed. So, uh, that sounds about right. I would probably lean towards probably the week of 12/1, which the Sunday would be 12/7. So probably the week of 12/1 to 12/7, that would be the face-to-face test three, and then the final is supposed to occur on. Oh, there it is. I see Proctor test three due by 12/7. Yeah, so that's it. And then the comprehensive final exam is on 12/10.
Okay,
And for
sounds
your class, that means you have to have it done by 12/10, but it's, it could be available earlier than that.
okay. And then for the final, we can still take it at the testing center, right?
Yeah, the testing center is what I have set up for, but yeah, I'll also have some times on 12/8 and 12/10 that you could use
Okay.
if you wanted to come take it under me.
Okay, sounds good. Thank you.
No problem. Thanks for asking. All
Sure.
right, well, guess we'll go ahead and get started. Anybody else have any last minute questions before I move along? All right, so when we were last here, we were working in conservation of momentum, and I had started example 913. So from your book, I'm going to read that again. I'm going to go ahead and share my screen so I don't forget like I do every day. I'll share it now because I remember. And yeah, well, all be proud of me for not having another senior moment, I guess. That's the way I'm going to pretend that I'm thinking you are thinking about it. So it's coming up now. I went ahead and rewrote some of the beginning stuff, mainly the three equations that are relevant for conservation of momentum and conservation of kinetic energy, which is the result. Conservation of kinetic energy is what results when you have an elastic collision, and the conservation of momentum is what results when the sum of the forces acting on the system is equal to zero. And this has two dimensions, so that's why I have one conservation of momentum in the x direction and one conservation of momentum in the y direction. So let me read over the question so everybody's on the same page. A proton traveling with a speed of 8.2 times 10 to the fifth meters per second collides elastically with a stationary proton and a hydrogen target, as in Figure 918. One of the protons is observed to be is observed. It's hard to pronounce a V right now. Observed to be scattered at a 60-degree angle. At what angle will the second proton be observed, and what will be the velocities of the two protons after the collision? So it is talking about protons. So I've written MA equals MB equals MP. In addition to that, what that means is I can divide both sides of this equation by M1 over, or by MP, I should say, which is the same thing as multiplying by 1 over MP. And in doing that, I will end up getting an equation that only has that has no masses in it whatsoever. What I'm also going to do is move this term over to this side and then square it. So what I'm going to do is I have MA, or in this case, it'll be, well, let me go ahead and, I'm going to go ahead and show the lines because otherwise I might throw you guys. So I'm going to say VA minus VA prime cosine theta A prime is equal to VB prime cosine theta B prime. Now I'm going to square both sides. And just to keep it separate from the other part, I'm going to write it in yet a third color. So this is going to be VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared cosine squared theta A prime is equal to VB prime squared cosine squared theta B prime. I'm going to call this equation 1. Now I'm also going to move, well, for starters, I'm going to go ahead and multiply both sides of this by 1 over MP. And I'm going to bring this over to that side over there. And then I'm going to go ahead and square it. I think I can do this without taking multiple steps. So I'll go ahead and write the result in red. And this will be equation 2. And what I'm going to write it in a weird place, but it's because I'm getting ready to add it with equation 1. So I'm going to get VA prime squared sine squared theta A prime is equal to VB prime squared sine squared theta B prime. Okay, that's going to be equation 2. And notice this is that technique that I told you guys you should memorize. In this case, we actually happen to have the case where the masses are all the same, so they all canceled out. But the same technique can work with the different masses as well. The big problem will only be basically that the masses would be in there in addition to the velocities, but you normally know the masses, so that shouldn't be too terrible of a problem. Now, in this case, in the conservation of kinetic energy, which is the part that's true because of the collision being elastic, in that case, I'm going to multiply by 2 ma on both sides. So that'll get rid of or excuse me, 2 over MP, and that'll get rid of the 1/2, and it'll also get rid of all the masses. So I'm going to say 2 over MP, and then of course, whatever you do to one side, you got to do to the other. So I'm doing the same thing over here. And what's going to be the result of that is I'm going to get VA. Ooh, I'm going to get VA squared is equal to VA prime squared plus VB prime squared, which I'm going to go ahead and solve for VA prime. So I'll go ahead and say VA prime squared is equal to VA squared minus VB prime squared like that. And I'm going to call that equation 3. So now we have the ability to actually solve this equation. What I'm going to do is add equations 1 and 2. So add 1 to 2. The whole reason I'm doing this is because the VA prime squared term in the equation 1 has cosine squared, but in equation 2 it has sine squared, but the coefficients are exactly the same, so I end up getting VA prime squared times just 1. So what I am left with though is the VA squared is not going to change at all. So I've got on the left hand side VA squared. I also have the minus 2 VA prime cosine theta A prime. That doesn't change. But as I said, when you add the VA prime cosine squared theta with the VA prime squared sine squared theta, the sine squared plus cosine squared can be factored out, and sine squared plus cosine squared is equal to 1. So in this case, I'm just going to get plus VA prime squared. And on the right hand side, I'm just going to get VB prime squared. Another student came in. So that's what I get from adding those two equations. Uh, I think I want to do this. I don't know if I want to. I don't know if I want to solve. I went ahead and just instinctively solved for VA prime, but I'm wondering if maybe I should have solved for VB prime. That might be a little nicer way of doing it. Yeah, I think I will do that. Let's. It doesn't matter. You could actually do it, but this will make it a little quicker. So instead of me solving that VA squared equals VA prime squared plus VB prime squared, instead of solving that for VA prime, I'm going to go ahead and solve it for VB prime. Technically VB prime squared. So VB prime squared is going to be equal to VA squared minus VA prime squared, and that's going to be what I call equation 3. Now I'm going to plug equation 3 into this new equation, which I'm calling equation 4. Oops. So this new equation is equation 4. So uh, plug 3 into 4. Now, it's just good note taking to be writing these sentences about what we're doing with each, because I can always go back and look at my work and make sure that I checked all, or that I used all three equations. Because in this case, we're solving for three unknowns and we have to use uh, three equations to solve for three unknowns. If we ended up accidentally not using one of them, we know whatever we got couldn't be right. So that's just a nice little checkpoint. So what I'm now going to do is I'm going to take equation 4, and the only thing that's going to change is really the VB prime squared on the right is going to be changed with VA squared minus VA prime squared. So I get VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared is equal to VA squared minus VA prime squared. Now, what you can see from that is the VA squared on the right will cancel out with the VA squared on the left. And I can also bring the negative VA prime squared to the left-hand side, where it'll become positive VA prime squared. And now the equation becomes negative 2 VA prime cosine theta A prime plus 2 VA prime squared is equal to 0. Obviously, that's a common factor of VA and 2 in it. So what I'm going to do is multiply both sides by 1 over 2 VA prime. And then I'm going to bring what's left to this side. So once I first multiply by all this, or actually, I will bring this to this side once I deal with everything else. That way I won't have any negative signs. So by getting rid of the 2VA prime, I end up getting negative VA cosine theta A prime plus VA prime is equal to 0. And of course, now that I bring the negative term to the other side, I'm going to get VA prime equals cosine, or excuse me, equals VA times cosine theta A prime. And from this, if I assume that theta A prime happens to be the 60 degrees, then we can figure out what happens with everything, and I'll solve that, and then we'll go back and look at it and see what happens if instead I chose to solve for this and then put the other angle, which we'll solve for already, in here and see what happens. So in this case, I'm going to go ahead and assume theta A prime is equal to the positive 60 degrees, in which case you're going to say VA prime is equal to VA, which is 8.2 times 10 to the fifth meters per second times the cosine of 60 degrees. And of course, the cosine of 60 is 1/2. So I know that VA prime is equal to 4.1 times 10 to the fifth meters per second. So that's part of the equation the what we're asked to solve for. Now I can go ahead and plug this into, let's say, equation 3, and that'll determine VB prime. So plug VA prime into 3. That gives me VB prime squared is equal to 8.2 times 10 to the fifth meters per second squared minus 4.1 times 10 to the fifth meters per second squared. So this gives me VB prime. Oops. This gives me VB prime is equal to, of course, I got to take the square root of all that once I do it, but I'm first going to take 8.2. I'm going to square that. The 10 to the fifth I don't have to actually deal with because it turns out when I subtract the 8.2 squared minus the 4.1 squared, it's not going to change it to be less than 1 or anything. So the 10 to the fifth is just going to be like a carrier on. So I'm doing 8.2 squared minus 4.1 squared. Uh, and that's going to give me 50.53. Now I'm going to take the square root of that, and that's going to give me 7.10. So basically, what I get is 7.10 times 10 to the fifth meters per second is VB prime. So I can go ahead and write that down as a solution for that. Now I can plug this into, let's say, equation 2. So plug this into equation 2, VA prime and VB prime into equation 2. And then what I get is we're going to get VA prime, which is 4.1 times 10 to the fifth. I'll leave off the units in this case. Squared times the sine squared of theta A, which we've already assumed the theta A would be 60 degrees, is equal to VB prime. And I might should have done this with the original form, but it's okay. It'll still work. This is VB prime, which is supposed to be 7.10. So 7.10 times 10 to the fifth, again, leaving the units off, times sine squared theta B prime. So when we do this, what we end up getting is, I'll write it up here because I'm running out of space. I get 4.1 times 10 to the fifth, and I'm going to square that, and I'm going to multiply that by the sine of 60. So I'll do sine 60 times, in this case, it became times, oh, I got to square it. So 0.8660 3 squared. Now I've got to multiply that by a sine of 60 squared. So times sine 60 squared. Whoa, Nelly. That was weird. Give me an answer that was not reasonable. Let's do this. zero point 0.7 times, let me see, sine 60. So if I square that, I get 0.75. And now I'm going to multiply that by the 0.75 that I got when I squared the other part. Oh no, that's not right. 0.75 is right. The 1.68. So I'm going to say times 1.68 times 10 to the 11th. Great, it typed it where I didn't mean to. So 1.681 times 10 to the 11th times 0.75 gives me 1.261 times 10 to the 11th is equal to 7.1 times 10 to the 5th. Quantity squared is 5.04. 1 times 10 to the 11th, and that's being multiplied by sine squared theta b prime. So what I have to do is take this 1.261 times 10 to the 11th and divide it by 5.041 times 10 to the 11th. And what we see is we get about 0.25. So this means 0.25 is equal to the sine squared of theta b prime. Now, technically, if I would have solved this, if I would have been smarter and not used the squared version, if I just would have used the 0 equals sine A, I would end up finding that the theta b would come out negative. But the way I did it this time, the theta b is going to come out positive, or it's actually going to come out as your choice of positive or negative. But in this case, the answer has to be negative. So it was just unfortunate that I used the version that I did. Specifically, I used this instead of this. If I'd used this and plug it in, it would have forced me to find the sine of negative theta, or the negative of the sine of theta b equals zero point 0.5. But the main thing is the result gives us theta b. Dang it, there I go, writing my phi again. The result is theta b prime is equal to negative 30 degrees. And that's a fundamental idea that you might would have put together if you looked at equation 3 before I solved it for VB prime. If you look at this equation right here, notice that looks like something that you might have learned in grade school. Do y'all remember anything that looked like this in grade school in math? Something that started perhaps with a P in the first word and a T in the second word?
Pythagorean theorem.
Exactly. So the fact that the VA squared is equal to the VA prime squared plus the VB prime squared suggests that one solution is clearly A and VA prime and VB prime being 90 degrees from each other. And in fact, that's exactly the answer. So in order for the first one to be plus 60, the other one has to be minus 30 because 60 plus negative plus or excuse me, I should say 60 minus negative 30 gives me 90 degrees, which is what's going to happen whenever you have two particles with the exact same mass colliding elastically. Their velocities afterwards will be separated by 90 degrees. No ifs, ands, or buts about it. Now, if you take into account the actual idea of pool balls, for instance, hitting and having some spin and stuff like that, then that's a whole different ball game. The angle doesn't necessarily work out to be exactly 90, but it still comes pretty close. Now, if in this case, what we did was go on the assumption that theta A prime was the 60 degrees, we didn't necessarily have to do that. We could have went ahead and tried to solve for VA prime and VB prime as we did, and then go back and put that number in, and we might have gotten theta A prime equals negative 30. And that came up, then we would have found theta b prime to be 60. That's all that's required for this one. So we now know all the answers to it. We've got it. Anybody have any questions on that? Okay, well, we're going to move along now. We're going to the center of mass part, and your book talks about the center of mass, and later he's even going to give us a long description of the center of mass and how we define it, and you can even make up Newton's second law in terms of center of mass and in terms of the system. That's what section 9.9 is all about. When you do that, what we discover is it turns out you can treat F equals ma as the equation, which I know I call it, I say F equals ma, but I really usually write it down as the sigma F equals ma. That's just a mnemonic that I use to remind everybody that it's not a particular mass, I mean a particular force that's on the left-hand side of Newton's second law. It's the sum of all the external forces that's on the left-hand side. So that's why I put that sigma in there. But the main thing is we've been studying that sigma F equals ma for individual particles, and a couple times I did choose it to be for a whole system, like in the Atwood machine, or in the case where I solved, three boxes that were tied together being pulled by another rope. That was a case where I treated the whole system as if F equals ma applied to it. What he's doing here in section 9.9 is he's working out the details, and he'll discover, and he ultimately does discover, that there exists an equation: the summation of the forces is equal to mass times acceleration, not for just a particular particle, but for a whole system. And in fact, it turns out to be that the system is the entire system, and it obeys Newton's laws in such a way that the center of mass is what's relevant. So, for instance, when we studied projectile motion and we found that the path of a projectile would be a parabola, what we actually are realizing as a result of this section 9.9 is that the projectile motion that we studied that gave a trajectory that was a parabola was in fact just what the center of mass would do. So if I, for instance, threw this pin like a ball, then what I'd find is one little spot somewhere on this pin would stay sort of stationary, and the whole pin would spin about that. And if you filmed it, you would see that one spot, the whole path staying in exactly the same place. You wouldn't see it switching or anything like that. It wouldn't even rotate smoothly if that was the case. So the center of mass is the thing that follows the parabolic trajectory. And in chapter 10, we'll learn about rotational motion. And that allows us to say, hey, if I know the pin left my hand with a certain angular speed in degrees per second or revolutions per minute or something like that, then if I knew its orientation when it left my hand, say like this, then I can calculate at any time later what will be the position of this around its center of mass, because it is rotating around the center of mass. Your book even has a picture of a crescent wrench being thrown, and it shows one spot on the crescent wrench is always following this sort of straight line, even though all the bits of the crescent wrench around it are spinning around. That's what's happening here. The center of mass is just following that nice parabolic trajectory, but this thing is going to spin according to the laws of rotational motion, which turns out to have another Newton's second law type version for it. And we could therefore in a very robust way. If I knew exactly what the orientation of the pin was when I released it from my hand, how high it was above the ground, and then the ground was level, or I knew exactly how high the ground was where it's going to land, that sort of stuff. And if I knew what its orientation was and how fast it was rotating, then not only could I predict exactly how high the center of mass went and exactly how far horizontally the projectile fired, I could tell exactly what position it was in when it landed. So it might land in this position, in which case we'd find that the pin tip touched the ground at a distance a little further than what the center of mass would have calculated as the range of the projectile. However, if it landed like this, say, then I'd find that this particular piece of the pin touched the ground before the center of mass got to the predicted range that we calculated, and therefore I would say that the pin actually landed short of it. I could also say exactly what angle the pin made, say, with the ground at the instant some part of it, whether it be the tip or this M, or it might have even landed flat. I can tell you exactly what that angle was. That's what we're doing going forward, at least in principle, though we're not really going to work too many problems at. But you now have all the tools necessary to do that once you cover chapter 10 and understand rotational motion. So that's what a lot of this chapter 9 center of mass translational motion stuff's about. So I'd like to run over some quick idea with you about thinking about the center of mass. So the center of mass is sort of one way you can define it is, if I want to find the center of mass of this Apple Pencil, then all I do is have to put my finger someplace and then move this until it balances all by itself. So I discovered that right there, which is pretty close to the center, but not exactly the center, uh, maybe a little bit off, what I've found here is the center of mass must be directly below my finger. In fact, if you had any shape whatsoever, let's say this shape right here, if we had this shape and we hang it from any random spot, let's say like this, then if I hung a plumb bob from that spot so that it made a nice vertical line, and then I traced that line onto this bob or onto this box, or used a chalk box, which is what you use in construction. You use a string line and you pop it, and that leaves a little chalk line that shows you a nice straight line that's vertical in this case. Well, that's what would happen here. I would hang it and it would make a nice line right across this box. Now, if I take and hang this box from any other spot, let's say right here, then I would drop another vertical line and trace that. And lo and behold, what I'd find is those two lines would cross at exactly the center of mass. Now, this is actually a three-dimensional object. See how it's got some thickness there? So technically, I would also need to hang it a third way and then see where that line crossed those other two lines. So maybe I'd hang it like this from this top corner, and that would make yet another line that goes down here. And then I just find where that line intersects with the two lines that went in front, and that would be the center of mass of this. So that's a way you can figure out the center of mass in a static way where you don't have to move. Another way, you just throw it and video it and find out what part appears to be rotating, whereas all the other parts seem to be revolving around that part. That would give you a definitive idea of exactly where it is. If you took the video and you measured it to scale and all that, you could figure out exactly where the center of mass is just by finding the part that's spinning about its center. So that's another way. Now, in terms of this pin balancing on my finger, if I went over 1 inch and hung a 10 kilogram mass from here, it would rotate that way. But if I went 1 inch over here and hung a 10 kilogram mass, then it would balance it right back out. Not only that, though, I could hang, instead of a 10 kilogram mass 1 inch away, I could hang a 20 kilogram mass 5 inches, or a half an inch away. And then over here, I could hang the 5 kilograms or whatever 1 inch away, or 10 kilograms or whatever I wanted to do. the fact is that if I multiply the distance times the weight, that gives me something that I recognize as torque. We haven't covered torque yet. That comes in chapter 8. But if you multiply the weight as opposed to the mass, because the mass is just a scalar, whereas if you multiply mass times g, you get the weight, which is a force and therefore a vector quantity. Well, if you had that, then the mass times g times the distance away from whatever you call the fulcrum, that would be the torque about that fulcrum. Therefore, you can think that if I want to find the center of mass, I want to find the one spot where all the torques around it, the ones that cause this rotation and the ones that cause this rotation, I would like to find out exactly where I'd have to place my finger so that all those torques add up to give me a zero torque. Well, that turns out to just be mass one times the distance away from whatever you called the arbitrary fulcrum, plus mass two times whatever distance you called from the arbitrary fulcrum, plus mass three, so on and so forth. In that sense, we can now say that the center of mass is given by this formula. So, okay, great. Oh, no wonder. I grabbed a pen for I had grabbed a pen for demonstration purposes and forgot that's not the one that's synced to my computer. So what we're going to have now is that X center of mass is going to be given by, normally it would be m1 times g for those torques that I was talking about, but it turns out the g is going to cancel out, and you'll see that in a second. So I'm going to say I take the m1 and I multiply by x1, which is the distance from the arbitrary point that you decided to be the origin. So I take that and I add it to mass 2 times x2 again, which is the distance from that arbitrary origin to where m2 is, and plus dot 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 on up to all of them, and I'll just assume that I have capital N of them. So that'd be m sub n times x sub n. And now I've got to divide all that because it has to have the units of x. So I've got to get rid of the m's. So what we divide by is m1 plus m2 plus dot 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 plus mn. So here's where you can see in practice, if I had multiplied m1 times g and m2 times g and m3 times g and m4 times g in the numerator, I'd have to do that in the denominator too, and you clearly see that the g's would just cancel out. The y center of mass is defined the same way, and I'll write it in the short algebra form to make it fit a little better. So it's the summation from I equals 1 to n of m sub I x sub I divided by the summation from I equals 1 to n of m sub I. So that's really the fancy way of writing it, but that's the center of mass. Now, if you, instead of having countable objects, this is like, people sitting on a log or balls sitting out on a plate or something like that. What if you wanted to find the center of mass of something like my calculator or a piece of aluminum shaped in the shape of a triangle? Well, then you have to imagine, instead of discrete things that are countable, you have to sort of imagine a continuous stream of material. And instead of summing things up, we have to do this one abstracted version of summing things up, which is the integral. So this is going to turn out to be xcm is going to be equal to the integral of x dm divided by the integral of dm. And YCM, by the way, I said what this was for X and Y. The Z is exactly the same, just we're going to be dealing with mostly just two-dimensional, so we ain't got to worry about that. But the YCM is going to be the integral of YDM over the integral of DM. And both of these are where DM is going to be equal to lambda times DL. R is going to be equal to sigma. That lambda is what we call the linear density or the line density. It's something that has units of mass per unit length, so it'd be like kilograms per meter. And if we're talking about something that's nearly one dimensional like this or a pencil or something like that, then and we assume it's a uniformly distributed mass instead of having, clumps of rock in it or something like that, then that lambda would be a constant and you could get it just by taking the total mass and divide it by the total length. However, if it's two dimensional, like a business card, for instance, that's a two-dimensional object. In that case, again, it's uniform, but you could take the mass and divide it by the area, and since it's uniform, that would be what sigma is. And in this case, it's sigma times the differential area element. Or if it's a three-dimensional object, then it could be rho times the differential volume. Now, in principle, if you had gone far enough in calculus, you could treat dA as just dx times dy because it'd take a double integral, or dy times dz, or dx times dz. All of those are optional, but we normally look for ways to do it with single integrals. So that's why we use like the method of washers or the method of cylinders and stuff like that. The same thing with rho dv. We could actually use dx times dy times dz. But again, we're not wanting to do triple integrals in that case, so we're going to find some other way, as you'll see. Now, before I move on, there's an example that your book does in section 9.8, and it's really quick. I don't want to waste the time to, well, quote unquote, waste the time. I don't want to spend the time to actually do it, as well as just what I'd prefer to do is just talk you through it. So, example 9.14, I'm talking about. So I'm just writing it here so you'll know it's one we talked about. It says three people of roughly equal mass m on a lightweight air-filled banana boat sit along the x-axis at position xa equals 1 meter, xb equals 5 meters, and xc equals 6 meters, measured from the left-hand end as shown in figure 924. Find the position of the center of mass. Ignore the boat's mass. Now, this is reasonable. If you've ever ridden one of these banana boats, you know it's just basically a vinyl material that you blow up with air. Air obviously has some weight, but it's not a huge amount of weight. And once you blow this thing up, it may weigh a few pounds, but nothing compared to actual humans. So it's fairly reasonable to do that. If, however, it actually weighed a lot, if it was completely symmetric, you just assume that the center of mass of it is dead center. So if it's 12 meters long, it'd be 6 meters across, or in this case, it's probably more like well, actually, it looks like it's more than 6 meters, so it's probably 3 meters out. If it wasn't uniform, you'd have to do calculations and figure out what the center of mass is, or do experiments. In this case, we got a person at 1 meter, so x1 is 1.0 meters, x2 is 5.0 meters, and x3 is 6.0 meters. So you know what's going to happen. I'm going to take m times 1 because that's the formula. It's m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. So if I take m times 1, that's 1m. M times 5, that's 5m. 1m plus 5m is 6m. And then if I take 6 times m and add that, I get 12m. So the x center of mass, the top part, gives me 12m. But now I got to remember that I got m plus m plus m in the bottom, so that's 3m. So lo and behold, I find that it's 4.0 meters is the center of mass. That's it. That's how difficult it is. So this is really a simple plug and chug problem. There's another one here as well, and it's example 915. Again, let me walk you a little bit through that. In this case, it says three particles, each of mass 2.50 kilograms, are located at the corners of a right triangle whose sides are 2 meters by 1.5 meters. So what we're looking at here is 2.0 meters is the distance from here. Well, I shouldn't have drawn it there, but anyways, I was drawing it like it's an axis, a mark on the axis. That's the 2.0 meters, and it's actually 2.00 even. And then the other one's 1.5 meters. Oops. So, uh, this would be right here, and then there's one at the origin. And each of these masses, this one right here, is 1.50 meters, like that. Now, each of these masses, M1 equals M2 equals M3 equals M, is 2.50 kilograms. So the x center of mass is just going to be, notice the x coordinate of the first one. This one's at zero point 0.0 meters, by the way. So in this case, I got M times 0 because the x coordinate of this guy is 0. Now the x coordinate of this one is 2, so I'm going to say plus M times 2. And the x coordinate of this one is also 2, so I'm going to say plus M times 2. And then I'm going to divide all that by 3M again because they're the same masses, so it came out to be 3. In this case, you see that 0 plus 2 is 4. So this is 1.33 meters is the x center of mass. The y center of mass is going to be, notice in this case, the y coordinate of this one is y equals 0, but it's the same for this one as well, whereas this one is 1.50. So in this case, I'm going to get 0 times m plus 0 times m plus 1.50 times m. All that's going to be divided by 3m. So I get 1.5m divided by 3m, and that's 0.50m is the y center of mass. So that's how easy these discrete ones are, and hopefully that's not a problem. When you do this last one, which was you'll see it's like a flat piece of aluminum in example 917. In that case, you just treat it as a rectangle because it's actually a Freeman square is what it looks like. So there's a L shape basically, and it goes like this. Well, you can break that L shape into one long rectangle, and then you can break the other part of the L into a shorter rectangle. And since they're uniformly made, that means their center of mass is their geometric center. So you just figure out the mass of each part and or what fraction of it is. And you'll see I've actually posted a couple good ones like that on my YouTube channel. I'll make sure they're in this week's module as well to help you with 917. So I'll just say check out example 917 and my video. Okay. I do one with a Freeman square that's just like this, only a little bit better. So now what I'm going to do is go into the more advanced aspects of calculating center mass using the calculus. So I'll start off with a fairly straightforward one. Let's imagine that, well, heck, I'll just use the example that the book has, which is example 916. Now, this example says, show that the center of mass of a uniform rod of length L and mass M is at its center. So I don't like writing that script L, so I'm going to write a L and a M are known. And we know the thin rod is uniform. Now, that uniform means basically, in this case, it's a thin rod, but still, What they're saying here is since it's a thin rod, it's sort of treated like a one-dimensional object. So if we took any slice, any vertical slice of this rod that's laying horizontally, if that slice was 1 millimeter wide, if we found another slice that was 1 millimeter wide, it would weigh exactly the same. If we found another slice that was 3 millimeters wide, it would weigh 3 times as much, so on and so forth. There's no part of it that has like a little rock in it that makes one little slice weigh more than the other. That's what we mean by uniform, and that normally translates to that lambda or that sigma are that rho. In other words, this quantity or this quantity or this quantity is a constant if it's uniform. Again, the lambda is kilograms per meter, the sigma is kilograms per square meter, and the rho is the normal density kilograms per cubic meter. In part B, it says determine the center of mass of the rod, assuming its linear mass density lambda varies linearly from lambda 0 at the left and to double that value at the right end. Okay, so that's the two parts we're going to do. I'm going to go ahead and draw a coordinate system. There's my x-axis. There's my y-axis. And what I'm going to do is say that this is my little rod, and I'm trying to show it as if it's essentially one-dimensional, very narrow. The length of that is L. The mass of that is big M. Okay. And what I'd like to calculate is the center of mass. So X center of mass is equal to the integral of X dm over the integral of dm. Uh, I will say that lambda, since it's uniform, is just going to be m divided by L. I'm not going to necessarily need that, but I try to calculate that every time because I know every semester my students sort of don't get what this lambda is, they don't get what the sigma is, and they don't get what the rho is. So I try to show it like this. Since it's uniform, this average value will be the value at every point. It's just m over L. So if you had another part that had a length little l, you could say lambda 1 equals lambda 2, which means m over, let's say the new part is equal to m over big L. So if you knew the little l, you could solve for m, or if you knew the little m, you could solve for L. That's the nature of it being uniform. If it's not uniform, then you'd have some kind of functional value. You'd have a lambda that changes as a function of x, and you'll see that in our next example. All right, the part B of this one. So what I'm going to do is choose my differential mass element, and that differential mass element is going to be right here. So it's that little purple slice. The width of that little purple slice happens to be, I'm going to make it differentially wide. The reason being is if you look at this integral right here, whenever you have an integral like that, if the integrand, which in this case is dx and to some extent dm, if that integrand has a dm that changes significantly from one part of or an x value that changes significantly from one part of dm to the other, then I'd have to go through another process where I'd try to find the center of mass of the differential mass element because I couldn't just arbitrarily call it x. So what you want to do is make a dm that has an x, which is the integrand, that changes only by an infinitesimal amount. So by me making this little differential mass element just infinitesimally wide and parallel to the x-axis like this, then I can say that width is dx and the distance from the left edge to the right edge is only dx. And if you sort of even went diagonal, it'd be dx, squared plus some infinitesimal y height squared square root, which again is very, very infinitesimal. So that's going to be my dx. And in fact, the differential mass element part of it, dm, is going to be lambda times dl. But in this case, the dl happens to be parallel to the x-axis, so I'm just going to call it lambda dx. So now I can go about working my two integrals. First, I'm going to do the integral of x dm is going to be equal to the integral of x. Oh, excuse me, I wrote dx there instead of dm. I didn't mean to do that. I jumped ahead of myself a little bit. So dm like this. And then the dm is going to be lambda dx. And now I see that I'm integrating with respect to x. So I'm going to integrate from x equals 0 to x equals L. Well, that lambda is a constant, so it comes out in front, and I get the integral from 0 to L of x dx. So in that case, I get lambda L squared over 2. Notice I went ahead and evaluated the integral. The integral of x is 1 half x squared, and then when I evaluate that at L, that'd be 1 half L squared, and when I evaluate that at 0, it'd be 1 half 0 squared. So I do 1 half L squared minus 1 half 0 squared, which just gives me 1 half L squared times the lambda that was already there. Now I'm going to do the same thing for the bottom integral. The bottom integral was just dm, which equals the integral from x equals 0 to L of, instead of x lambda dx, it's just lambda dx, which equals lambda times the integral of dx is just x. So that's going to be lambda L. Now we can see that the x center of mass is going to be equal to lambda L squared over 2 divided by lambda L. And you can see that the lambdas clearly cancel out. The L cancels out with one of the L's. So I'm just left with exactly what we were asked to prove, L over 2. So that was part A. Now, part B, they said lambda equals L0 at x equals 0, and lambda equals 2 lambda 0 at x equals L. So, and they said it varies linearly. I'll read the wording for you again in a second. So it says determine the center of mass of the rod, assuming its linear mass density lambda varies linearly from lambda equals lambda 0 at the left end to double that value, lambda equals 2 lambda 0 at the right end. So I'm going to say that lambda of x is equal to lambda 0 over L times x. Notice that if I get to x equals L, that would just give me a lambda 0. But if I add to that a lambda 0, then at x equals L, I will get lambda 2 lambda 0. And at x equals 0, I'm just going to get lambda 0. So this exactly matches the criteria. Plus, it has the form y equals mx plus b. So it does vary linearly. So that's what we're going to do. Now I'm going to go ahead and calculate that. The x center of mass, again, is the integral x dm over the integral dm. The integral of x dm is going to be just like I had before, except now I have lambda that is a function of x. Everything else will be the same, though. So I'm going to say the integral from x equals 0 to L of x times, now I'm going to substitute my lambda formula, which is lambda 0 over L times x plus lambda 0. All of that is basically lambda, so I multiply lambda times dx, which is what we did before. Now we've got that. Now you see that the lambda 0 is the constant that can come out front. So I'm going to put that out in front and say I got an integral from 0 to L. Now I'm going to distribute that, and that's going to give me 1 over L x squared plus 1, or actually I'll leave off the 1, plus just x. and then dx. So that integral is pretty straightforward. I've got a lambda 0 out in front, and then the integral of x squared is 1/3 x cubed. And when I evaluate that at L, that's going to be 1/3 L cubed. And I've already got a 1 over L by it. So I'm going to say 1 over L times L cubed over 3. Now the integral of x is x squared over 2. Evaluate that at L. That's going to be L squared over 2. So that's going to be L squared over 2 here. You can see that this L in the bottom cancels out that, leaving a 2 up there, which means I can just pull the lambda 0, or excuse me, the L out with the lambda 0, the L squared, in fact, and I got that times 1/3 plus 1/2. Well, that's the same thing as 2/6 plus 3/6, getting a common denominator, in other words. So I end up getting 5/6 lambda 0 times L squared. So this is 5/6 lambda 0 L squared. Now I've got to do the integral from 0 to L. Well, actually, I'll leave that off right now. I got to do the integral of dm, which equals the integral from x equals 0 to L of lambda, which in this case is lambda 0 over L times x plus lambda 0, all that times dx. Again, I can pull the lambda 0 out in front, and I get the integral from 0 to L of 1 over L x plus 1 dx. Now the integral of x is 1/2 x squared, so this is going to become lambda 0 times uh, L squared over 2L plus the integral of 1 dx is just x, so that's just going to be plain L, like that. You can see again that the L in the bottom is going to cancel out the exponent of 2, and I'm going to again have a factor of lambda 0 times L, but this time I'm adding 1/2 plus 1, which gives me 3/2. So I get 3/2 lambda 0 L. So my x center of mass is going to be this top one, which was 5/6 lambda 0 L squared, divided by this bottom, which is 3/2 lambda 0 L. Notice how I didn't actually have to use the lambda 0 at all, just like I didn't have to use the lambda last time either. What's going to happen here is I've got 2/3 times 5/6. So this is going to become 5/6 times 2/3. 6 is in fact 2 times 3. So I can now see that this 2 is going to cancel out with that 2, and that's going to leave me basically 5/9. But I still have the L that survived, so my answer is 5/9 L is equal to the X center of mass. Which, since the density doubles from one end to the other, we would expect it to be a little bit further from halfway. And sure enough, 5/9 is a little bit further than halfway, because halfway would be 4.5/9 of L. So in this case, we've got 5/9, which is slightly bigger. Anybody have any questions on that one? All right, well, let me show you another one. This is a little more advanced, and it's one that the book has these types of problems for problems at the end of the chapter and occasional problems in the homework, that sort of stuff. But they don't really do them in the examples, so I try to give you a little bit harder examples so you'll know exactly how to do this stuff. Not only that, this is exactly the process you do in statics, If you're taking a calculus-based statics, you'll learn that you have to use these integration techniques to find the centroid of force and also to find the net force, because it turns out you have to take the force density in some sense and integrate that just to find out what the net force is. So, for instance, you might, load a 2x4 with a load that's zero at the left end but goes up to some W at the right end. That's a triangular load. And in order for you to figure out where that total load acts like it's acting, you have to find the centroid of the force in that case, which is just like finding the center of mass. So I'm going to do that now. This is one that's just made up. Okay. So I'm going to find the x center of mass and the y center of mass of this shape. The shape is going to be something like this. This is what we'd call a homogeneous lambda. That's what they do it in your calculus class. Probably the end of chapter two, or excuse me, the end of calc two. Uh, they're normally covered it by the end of calc two. In this case, this is what we're looking at. A homogeneous lambda just means it's uniform. Homogeneous means it's uniform. And then the lambda part means it's two-dimensional. Just like a sheet of paper, it has a macroscopic width and a macroscopic height, but the thickness is infinitesimal compared to those. So that would be an example of a homogeneous lamina, as close as you can get to it. Okay, or if you take a sheet of graphene or something like that, that would be literally one atom thick. So that'd be even more like a homogeneous lamina. But the main thing is we're going to treat it as if it's uniformly made, so that's why it's homogeneous. I'm going to go ahead and draw a coordinate system to make use of it for my integration process. There's my y-axis, there's my x-axis. The width of this is just going to be w, and the height of this is just going to be h. And in addition to that, I'm going to say its mass is m. And since it's two-dimensional, I will say that sigma, the two-dimensional area density, if you will, is just m over 1/2 w times h, because the area of a triangle is 1/2 base times height. So you could also write this as 2m over wh. Again, we're not necessarily going to need it, but it's good for you to understand what this sigma is. So that's what I'm going to do. That's the density per unit, or actually the mass per unit area. Now, again, the formula for the x center of mass is the integral of x dm over the integral of dm. So again, we're trying to do an integral of x over dm, and I need the dm to not have a significantly different value of x at one point than it does at another. So what I'm going to do is choose a vertical rectangle. So there's my vertical rectangle right here. I'm going to say the width of this rectangle is just dx, and I'm going to say the height of this rectangle is y as a function of x minus 0, so it's just y of x, where y of x is this. The equation for that hypotenuse of this triangle is actually going to be h over w times x. So that's my y of x. Everybody follow that? Anybody have any questions on that? Now I can say that dm is going to be sigma times dA, but that is sigma times y of x times the width dx, like that. So notice y of x times dx is my dA. Now I can do my integration. The integral of x dm is equal to the integral of x times sigma times h over w times x. There's my y of x times dx. And now we see we're integrating with respect to x, so that's going to be from x equals 0 to w. Now, obviously, the sigma, the h, and the w are all constants, so I'm going to take the sigma, h, and w and pull it out in front. And now I'm going to get the integral of x squared dx from 0 to w. And that gives me, since the integral of x squared is 1/3 x cubed, that's going to give me sigma h over 3w times w cubed, which gives me sigma h w squared over 3. Now I'm going to calculate the integral of dm. So the integral of dm is going to be the integral from 0 to w of just the lambda or sigma times dA, and that was h over w times x times dx. So again, I get sigma h over w out in front, and I just get the integral from 0 to w of x dx, which gives me, of course, sigma h over 2w w squared, because the integral of x is 1/2 x squared. Again, this gives me sigma h w over 2. So the x center of mass is sigma h w squared over 3 divided by sigma h w over 2. Now, here's the part where I tell you the rule is when you have a triangle, the center of mass, if it's a uniformly distributed mass on the triangle, the center of mass of the triangle is always 2/3 of the way from the narrow part towards the wide part. So if we're imagining going from the narrow part of the triangle, which is here, along the x-axis, that's our x center of mass. Then if I wanted to go to the center of mass, I'd go 2/3 of the way from the narrow part to the thick part, so I'd expect it to be 2/3 W. And lo and behold, what you see here is we get 2 over 3. The sigma cancels out with the sigma, the h cancels out with the h, and the w cubed, uh, that's supposed to be a w squared, I think. Yeah, that's supposed to be a w squared. Let me fix that real quick. The w squared is going to cancel out with the W downstairs, let's just leaving a W on top. So it comes out to be 2/3 W. Now, given that rule, we're going to have to calculate the Y center of mass. That's going to be a little bit more complicated. But notice I can predict what the answer is going to be. I want to go from the thin part towards the wide part. So I'm going to start at this part up here because that part's the thin part. And I'm going to move to the fat part parallel to the y-axis. And I want to go 2/3 of the way. So 2/3 of the way down is 1/3 h. So we expect this answer to be 1/3 h. So expect YCM to be 1/3 h. Now let's work it out. YCM is going to be equal to the integral of y dm over the integral of dm, right? Now, I need to redraw this real quick just because it's a little bit messy otherwise, because I need to draw another rectangle on there. So what I'm going to do is say this is my y-axis, this is my x-axis, and this time I'm going to draw here, here, and here. This is H, this is W, that's M again. But what I need this time is I need a rectangle that doesn't change much in Y over the whole DM. So with that in mind, I want to make a very thin horizontal rectangle like this. And it's thin because the difference in Y from one side to the other must be infinitesimally small. So that thickness is going to be dy. And then the height, on the other hand, is technically going to be w minus x of y, where this right here is a function x of y, which I guess you can probably recognize as w over h times y. Notice I'm just solving for x and the y of x that I used in the first part. So I can go ahead and complete my integrals as follows. The integral of y dm is going to be equal to the integral from 0 to h of y, and then my dm is equal to sigma dA, which is going to be equal to sigma times w over h y times dy, meaning this part right here is the dA. So I can go ahead and write sigma w over h y dy. I can pull all that junk that's constant out in front, so I'm going to get sigma w over h out in front, and I'm going to integrate from 0 to h of y squared dy. That gives me sigma w over h times 1/3 h cubed, which gives us sigma w 8 squared over 3. Now, in principle, I could just take the sigma dm from the previous one, which was sigma hw over 2. But one of the nice things about this, when you make up this check, if you don't get exactly what you got before, then you know you might have screwed up a little bit in choosing your differential mass element or something like that. So I'm going to go ahead and do the integral anyways. So the integral of dm is going to be the integral from 0 to h of sigma w over h y dy, which is sigma w over h times the integral y dy from 0 to h. That's going to be sigma w h squared over 2h, which gives me sigma w h over 2. So the y center of mass would be sigma w h squared over 3 divided by sigma w h divided by 2, which in this case, whoa, what's going on here? I'm getting 2/3 instead of 1/3. I did this today and got 1/3 like I was supposed to. Did that right. 1/2 y squared. Oh, I know. Everybody, I wrote it correctly, but I didn't do it. I said right here w minus x, but I forgot to write that in here. So that's what went wrong. Let me kill this. I'm going to fix this real quick. Actually, the way I'll fix it is so y'all will still see this in case you need to. I'm going to copy this over to the next page. copy. I'm gonna copy that over to the next page and fix it there. Okay, so what's going to happen is all this is W minus X of Y is what I'm supposed to be doing there, and I just forgot and wrote it wrong. So it's sigma, whoa Nelly, it's Y times sigma times W minus, now in this case, it was the W over H y like this times dy. That's what went wrong on the other one, and that's why I'm getting the wrong answer here. So we'll fix this in a second, but it shouldn't be too hard. Sorry about that. I know I said it right, but that doesn't matter if you don't actually do it right, which is what I did. So, anyways, here's the correct part. So I can pull out a sigma and a w on this, and that's pretty much it. So it's going to be sigma W integral 0 to h of, now I'm going to distribute that y. It's going to be y minus 1 over h y squared dy. That's going to give me sigma w. The integral of y is going to be 1/2 y squared, so that's going to be uh, h squared over 2 minus, this one's going to be 1/3 y cubed, so it's going to be h cubed over 3h, like that. We can see that that's going to be sigma. Notice this cancels out with this, leaving a 2 there. So I'm going to say this is sigma h squared times w, because the w is already there, and then I'm going to get 1/2 minus 1/3, and that of course is 3/6 minus 2/6, which is 1/6. So the answer here is sigma w h squared over 6. Now I'm going to do the integral of dm. Sorry about this, folks, that was a pain. The integral of dm is going to be the integral from 0 to h of sigma w minus w over h y dy. I can factor out the sigma w, and I'm going to be left with the integral of 1 minus 1 over h times y dy from 0 to h. That's going to give me sigma w times h, because the integral of dy is just y, and then I evaluate that at h, and then 1 over h times the integral of y would be h squared over 2, like that. So you can see that this h is going to cancel out with that one over there, and in fact now I can say I've got sigma w h times 1 minus 1/2, and of course that is sigma wh over 2. So sorry about that diversion, but now I can take and put the numerator up top, sigma wh squared over 6 divided by sigma wh over 2. That's going to give me 2 over 6, which is 1/3. And then notice the sigma w cancels out with the sigma w, and the h squared cancels out with the h. So I just get 2/6 h, which is 1/3 h, which is what we expected. So that's it. And you can see how by actually doing that, I caught my own error, which was the whole reason I told you to do that. So that's it. We finished chapter 9. We'll go into chapter 10 next time. I'm sorry I went about 2 minutes over, but you guys are free to go. I'll wait till the last person leaves in case anybody has any questions. Hmm.
I actually do have a quick question. It's
Yes,
about the
ma'am.
test we had earlier.
Hmm.
That question where it was the point
Hold on a second. Hold on a
between.
second. Hold on a second. Hold on a second. This is a test question, and there's some students that might not have taken it yet. So
Oh, sorry.
I don't want to give you that, but I can do a breakout session. I can put us in a separate room, and you can talk to me about it if you'd like.
Yes, please.
Okay, hold on a second. Let's say, see if I can figure out how to do this. It's been a while since I've done it. Breakout room, breakout room, breakout room. Participants, poll layout. Anybody else have any questions while I'm waiting on this?
Um, I had a not similar question. I
Okay.
just noticed when I was taking the exam, some of the questions were very familiar
Uh-huh.
from exam one.
Yep.
Is it all like cumulative, like it all builds on itself?
Yes, that says it. It says it in your syllabus, and I've told you numerous times. Basically, every test and every practice test is cumulative. Specifically, if I find something that bites my students in the rear in the first test, meaning like 60% of the class doesn't get it right, then I usually put that on the second test, and if they still don't get it right, I put it on the third test. So that's a big deal. Actually, Jaden, can you give me a call right after this and we can talk on it by phone, or do you need the actual Zoom? Because I can't figure out right now where the
That's
heck
fine.
my
I was
chat
just
room
gonna
is.
email you afterwards, just in case, because I know
Oh, that's
some
fine
people
too
would
if you want
say
to
this.
do
Yeah, I
that.
was just gonna email you.
Yeah, no problem. Yeah, I
Okay,
can talk
cool.
to you about whatever that is. I'm having a hard time finding the breakout session, so I apologize.
No big deal. That's all good. Thank you
Okay,
though.
no problem. Anybody else have any questions? Are y'all seeing a pink line drawn across my notes here? Because all of a sudden that appeared and I don't know what happened, but evidently it came from somewhere. Makes me feel like I wrote on the screen. Melanie, did you have a question?
Yeah, I had a quick question
Yes.
on the very first problem that we did.
Hmm.
Um I like the last step, I believe.
I think it was this one. Yes.
Yeah, yeah, that one. I think. Yeah, it was. Because right before we found theta b prime,
Uh-huh.
where did the 5.04 times 10 to the 11th come from?
Okay. That is actually when I took this part right here. Excuse me. Make sure I got the marker right. This right here,
Hmm.
8.2 squared times 10 to the fifth squared minus 4.1 times 10 to the fifth squared gave me that quantity.
Okay,
It's the square of VB prime, basically.
got it. Okay.
And it was stupid because I blindly looked up here and took this, or excuse me, blindly looked up here and took this instead of taking this. If I'd done that, it would have been a lot less complicated. You wouldn't have seen all the squares, and you would have got the negative sign that was supposed to be there. So that was just a boneheaded excuse for screwing
No,
me.
you're all right. I understood it. It's okay. I just wanted to, I got lost for a second there because I didn't know where that number came from. Okay,
No
perfect.
problem. Well, is that
That
it?
was it.
All right.
Yeah, that
Well,
was
you
it.
have a good day. Thank you very much for coming.
You too. Thank you. Have a good weekend.
You too. Bye bye. Stay safe.
Bye.
Bye, everybody.